All right, we're recording. All righty. So, whoops, gotta click back. So, welcome everyone. This is the second HKN IEEE Tech Talk of the semester. This one is Introduction to Stealth Technology, presented by me. We already hit this one. All right, quick introduction, real fast. Who am I? I am a graduate student. I'm a graduate of the undergrad electrical engineering program here, currently working on my master's. I am a full-time software engineer at Northrop Grumman on the GWS program. If you want to know what that is, you can go on Wikipedia and look up ground-based mid-course defense. It'll give you all the information about what that is. I am a habitual project collector, as you can see by the explosives, the 150-watt laser, and also a rocket enthusiast goes in there as well. That's me on the Northrop Grumman website because I'm a special boy. All right, so expectations and what to expect. So today we're going to go over Introduction to Stealth Technology. It is an extraordinarily broad field. This entire presentation is built off of a small portion of this textbook, which is Radar and Laser Cross-Section Engineering by one David C. Jen. It's about $109 on Amazon. If you have a remote interest in this kind of stuff by the end of this presentation, work in aerospace, defense, interested in aviation, electromagnetics, this is an extremely useful textbook, not just for stealth and radar purposes, but it is a really good way to learn a lot of other fundamentals. So I highly recommend it. It's in my personal library. You can tell because I put my goofy crest thing in the page. All right. So first, we're going to go over a quick understanding of what is stealth and why it's important, why everyone cares about this so much. Next, we're going to do a brief history of stealth, starting all the way back to, putting a bush over yourself and hiding. Not too long. And then we're going to go up to the modern day stealth coatings and stealth technology that everyone's somewhat familiar with. I'm sure there's going to be some things I say here today that you did not know were important, but you will very quickly learn that they're extremely important. There's a slide about the three-ish senses where I'm going to talk about detection techniques besides radar that have to be taken into consideration, but radar is the single most important detection technique that anyone uses. So we will be emphasizing that, and that is what most stealth technology is directly focused on mitigating. Then we're going to do a brief discussion about optics. There's a disclaimer, and then we're going to go right into the big ticket items, radar cross-section, target shaping, and radar absorbent materials. And then we'll have a Q&A basically the rest of the time. I'll stay here as long as I need to answer any questions that anyone may have. All right, so let's get it moving. So what is stealth? And why is it important? Stealth is very broad. It could mean hiding from sight. It could mean being quiet. But for our purposes, stealth is strictly utilizing various mechanisms, physical properties, and technologies to minimize the detectability of a vehicle. It doesn't even need to be a plane. We'll be talking about planes and aviation vehicles primarily today, but we do this with boats. We do this with ground-based vehicles, tanks, cars, not to the same extent, but planes are the most important, but we do it with a lot of stuff. And basically, the reason this is important is because modern radars and modern missiles are really, really good. Gone are the days where you would have two people in an aircraft fly over the horizon, see each other, and get into a dogfight. That is not how this goes anymore. If you do not have an adequate stealth coating or stealth systems, you will be shot out of the sky by a missile from 2,000 miles away before you even see another plane. Nowadays, stealth is survival, straight up. If you do not have stealth technology and really just stealth technology implemented to your vehicles, you will lose the engagement, straight up. Air defenses will see you early, our early warning radars will see you, our missiles will be able to track you, you're done. So, it is not a feature, but a requirement. So it's extremely important. Every aerospace vehicle that the United States produces has stealth in consideration. Some more than others, but every vehicle takes into consideration stealth and radar observability. All right. History. So the concept of making things hard to detect has been around forever. Ghillie suit, camouflage, we've been doing this for a long time. Nature even does it. So it's very important and very valuable. But for our purposes today, stealth began around World War I, where we started with just camouflage paint. You would paint a vehicle, you'd paint boats and planes to match their surroundings, make them harder to view with your eyes, because at the time, radar was not in play yet. But radar and sonar came to being around World War II, and now the game was different. It was no longer about eyesight. You could start seeing people at night, over horizons, underwater, and everything got far more complicated very, very quickly. One of the three fundamental technologies that won the Allies World War II was radar. And if anyone's ever heard the concept of carrots improving your eyesight, that was a lie that the British made up to trick German pilots. Because the Germans were like, why are we getting shot down at night? How are they seeing us? So the British leaked intelligence reports and said, hey, we're feeding our guys more carrots. That's how this works. And they started eating carrots and kept getting shot down. So that's how that goes. But of particular interest, cloaking aircraft from air radar became a top priority post-World War II. Once radar, the secret got out, everyone started making use of it, and now it was all about keeping your vehicles invisible from radar. With the first efforts of this being undertaken in an attempt, they failed horribly, to reduce the radar cross-section of the U-2 spy plane. If I were to ask you what's the first stealth plane ever invented, a lot of people may say that. No, that thing was terrible. Its solution was to fly 70,000 feet in the air, and they hoped that the radar did not have the range. It had the range. They just couldn't get to it, because no other plane could fly that high. So, in 1958, the CIA began development of the A-12. It's a variant of the famous SR-71 Blackbird, and this was designed similarly to the U-2, to avoid radar by flying high and fast. Still, no notable stealth coatings or RCS mitigation technology. Well, you'll notice this in a bit when we start talking about RCS, but this thing would light up like a Christmas tree if you hit it with a radar, which is not good. And then, the first vehicle, so this is the fun fact for the evening, the first stealth vehicle from the United States and in human history is the F-117 Nighthawk, this polygon-looking thing. And basically, it was the first aircraft designed around stealth. Its only method of survival was stealth. It had no weapons, it had no flares, it flew slow, it flew low. It was only good at avoiding radar detection. It had 2 GPS-guided bombs in its bay that would it use to hit high-value targets behind enemy lines, and then it would scurry away and hope it can't get intercepted. One of these was shot down during the Serbian War, and Serbia never let us forget that one. All right, 3-ish senses. There are 3 main ways, really 2, but there's a third one that is accounted for submarines and such. 3 signatures that are used to detect vehicles, aircraft, etc. Radar returns, by far the most common. Thermal emissions, which, while not as common, are useful. And there's an entire field of electro-optics and infrared technology that's actually extremely important for this. Missiles make heavy use of this type of stuff. We have space-based sensors that make heavy use of this type of stuff. Not really for aircraft tracking, because radar provides far more precision, but we do have it. And then acoustic emissions. This is more sonar, that kind of deal. You don't really see acoustic being used against planes, although it can be. Planes are actually pretty loud. But this is not an exhaustive list. There are other methods. As mentioned, things can emit electromagnetic radiation. Anytime a circuit turns on, anytime a message is sent, most planes are fly-by-wire, which means the computer's doing everything. Electromagnetic emissions are coming out of that. With a sufficiently advanced detector, you can track it. The United States, we're really good at that. Everyone else, not so much. All right, so we're going to start by breaking down these senses. So for those who are unfamiliar, radars are basically an antenna. And all it does is it emits an electromagnetic wave in the form of a radio wave, and it'll go out, bounce off of a target, and reflect back. And all you're doing is timing that. Based on the time, since you know the speed of this wave traveling, you can immediately calculate the exact distance away. Then you can use tricks like the Doppler effect to calculate its speed. You can use the known position of the antenna, along with the phase angle of the return, to figure out its orientation. And then you can start doing a bunch of extra stuff. That's where signal processing comes into play. That's a big business in Huntsville. That's one of the main businesses for the electrical engineering program, signal processing and radar. Radars have become so advanced and precise that they are the core of every nation's sensor infrastructure. Bar none. Nothing else is more important to a nation than its radars. You would be, if I had a map, I don't know if one exists, of every radar that is known in the United States FOV, like its POV, what it's possibly able to see, it would probably look like a very large mess of overlapping colors because of how many radars are at play at any given time. And if anyone's ever seen this thing before, very famous boat, it's actually a boat. Huh? Yes, the sea-based X-band radar. That guy is really funny. He's very large. Under that radome, there's a massive phased array antenna. That thing can see into extremely deep space and has an extraordinarily precise field of view. All right? There are many types of radars. Land-based early warning. These things are about the size of whole buildings. Airborne. Northrop Grumman actually makes this vehicle. That is a radar. Seaborne. That's a Aegis battle system ship. And then there are actually some spaceborne systems that are coming into play nowadays. Normally, you like to put infrared systems up in space, but people are starting to catch on that radars up there might be pretty useful as well. So things like this can scan massive swaths of the entire Earth every second. And they do, constantly. Now we're going to move on to the thermal emissions real quick. This is called a SBIRS, space-based infrared radar. Infrared system or sensor. Yeah, SBIRS, space-based infrared sensor. There's several of these orbiting Earth at all times. These are used to detect ICBMs coming up. The famous AIM-9X heat-seeking missile, and that is an electro-optical infrared sensor system. These are often built into aircraft, missiles, the works to help them track things. But, as we all know, aircrafts fly. How do they fly? They have engines. What do engines do? They burn fuel. And therein lies the problem with thermal emissions. It doesn't matter how stealthy your vehicle is, how well it reflects radar, you're emitting thermal radiation, which is not great because it's detectable. Now, because we have an atmosphere, it gets attenuated pretty heavily. So most of the time, you're safe. But there are still considerations to be made. And if we actually go back real quick to the F-117, if you look very closely, its inlets are covered in grates. And if you look at the back, it doesn't have like an outlet as you would expect. It has a long slit instead, which allows the air to expand and cool before it exits the vehicle, which makes it harder to track this thing with infrared sensors. So that was a super important consideration to be made there. But we're not going to be talking too much about these. That was just a good example. And then this one is just funny, which is acoustic emissions. Prior to radar, this is the type of stuff people would do. They would sit up inside these goofy things and aim these big horns out, listening for engines and planes and stuff like that. We don't do that anymore. That's dumb. All right. This is important. We're about to get to some... Basically, all this stuff is just a prelude. We're about to get to the stuff in the book. So if you have a notebook for that, it might be helpful if you want to remember some stuff. But when it comes to this stuff, radar, electromagnetic radiation, it is far more complicated than really a human can really conceptualize easily. We have a lot of models and systems and ways to try and explain it, but it's still just too complicated. So we like to make analogies to simplify things. In the case of radar, we're going to make assumptions and analogies and treat it as if it's a laser, beam of light. So, in that case, there are 4 things to consider. What happens when you shoot light at something? It can reflect, it can transmit through it, it can absorb, and it can scatter. These are the 4 things that are very important to remember, but for radar purposes, we are particularly interested in reflection, absorption, and scattering. Transmission, not so much. As you can see down there, this is important for RCS and RAM, which is radar cross-section and radar absorbent material. All right, it's time to get into the good stuff, so I have to hit you with the disclaimer first. I do not have access to any classified technology regarding stealth. I promise. I will not be leaking anything today. I will not be leaking anything today. All right, so basically this is just so the men in suits don't harm. All right, time to have some fun. We shall begin with the messy world of RCS, radar cross-section. In order to understand radar cross-section, we must provide a foundational understanding of how radar works. So it is equation time. So, we're going to break this down to the best of our ability, try and make it easy to comprehend. So, there's this concept of power density at a target. I probably should have put a picture up there, but there's pictures later. All right, so what you've got there is power density at a target. which is what we're interested in. We want this to be pretty high, because the higher this is, the more it comes back to us. Now, the issue, this power density at the target will then, upon hitting the target, scatter back to us and become a power density scattered back to the observer. We will then relate the power density just into sheer power in watts. Nothing too crazy, but let's just name some terms here. So the power density at the target is a pretty simple formula. PT is the power of the transmitter. Everyone knows a 120 watt light bulb? 120 watt transmitter, same deal. Instead of emitting 120 watts of light, it's emitting 120 watts of radio waves. Simple enough. GT is a concept called gain. In this case, let's say you had a circuit generating your signal, but it's not a high power circuit. It generates a signal that's 1 watt. Gain is basically just a multiplicative factor. It just boosts the signal up. If you've ever heard of the term an amplifier, that's what this is doing. It amplifies the signal. Now, in this case though, that's not the gain of an amplifier. That's the gain of the transmitter, which is antenna gain. We're not going to get into antenna gain here because it would just revolve us going deep into electromagnetism and then antenna theory. We're not going to do that. Just know that gain just means you boosted a signal. That's it. Realistically, antenna gain in this case means the difference, the ratio of if you were to just have a signal emit equally in all directions like an isotropic shell, gain would be the difference of that versus how your transmitter shapes your energy out. Basically the proportion of how much energy is lost equally versus your system and how much of its energy it focuses like a laser, right? But just think of it as a multiplication factor. Everyone knows 4 and pi, I hope. And R is simple. It is just the distance between you and your target. All right, so we've got those down. Now, that is what hits our target, which is the power density at the target. So that formula just tells us I hit the plane with this much energy. Then this tells us how much energy comes back to me. And this, as you can see, is Wi here times this factor, which is actually 4 pi r squared again. This little symbol right here is sigma, but it's actually RCS. So that sigma just stands for your radar cross-section, which is in meters squared. Nothing too complicated yet. Which results in your power transmitted times the multiplication factor times the square area in meters with this factor down here. 4 pi r squared, whole thing squared. All right, now we're going to relate this back from that power density, kind of hard to conceptualize, and just bring it back to sheer power in watts, same type of power you pull out of a wall. The power that's received back at me is the scattered power just times the area, the effective area of my antenna. As you would expect, if a light bulb emitted energy, the bigger a reflector you have, the more of that energy you can capture and focus it. That's all that is, conceptually. Now, the effective area of the antenna, this AER term, is actually its effective aperture, but it's just basically how much of the antenna is going to be experiencing that electromagnetic wave. All this is the effective. That's because antennas have efficiency factors. If your antenna sucks, your effective aperture is going to be way lower because it's terrible. If it's perfect, this is just equal to the area of the antenna. Let's assume it was a plate, it'd be the exact area of that plate, length times width, nothing crazy. Then we have the receiver gain relation. Again, that gain term. When you emit 120 watts, let's say, of radar, you're not going to get even close to 120 watts back. That is going to lose so much energy through the atmosphere, get absorbed, reflected, refracted, scattered, come back to you, lose even more energy through the atmosphere, and if you sent out 120 watts, you'd be lucky to get 1 milliwatt back. But we have sensitive antennas. We can detect it. But to be useful for signal processing, we need to boost it. That's all this is, the receiver gain. But again, it's the gain of the antenna, which is complicated again. Just think of it, it's just it's a scalar value, no unit, just a multiplicative factor. But as you can see, it's a relationship between that effective area, that aperture, and this is wavelength. Everyone's heard radio wavelengths. You've got your frequencies, 10 gigahertz. A quick way to remember ups and downs of frequencies is if you have 300 megahertz, the wavelength is exactly 1 meter. So then up from there, below from there, the higher frequency you get, the smaller your wavelength. Lower frequency you get, the longer your wavelength. Wavelength's just in meters, and that's just squared. So you're going to start seeing here that this in the denominator is going to become a problem later on. And then we finally get to go to our full received power, which is the power I shot out, times the gain of what I shot out, times the gain of what came back, times my radar cross-section in meters, times that wavelength squared, all divided by this massive r to the 4th power. So also what's important to note, the word monostatic here, if your radar sends out a pulse, transmits it, and then the pulse comes back and you receive it in the same place, the same antenna that shot it out listens to it, that's monostatic. Just means same place. There are other systems and other types of radars called bistatic, multistatic. Those types of systems complicate this tenfold because they're way harder to deal with. But we're not doing that. This is introduction. So received power, no, down here. But because it's monostatic, the gain of the transmission and the receive are identical. It's the same antenna, same multiplication factor. So you can just set it to G. But again, in this case, you could replace this with G squared if you want to. But it's better sometimes to leave it be. So then there's one last thing. The final formula is received power with processing gain and loss. Processing gain is actually an amplifier. You have a circuit, takes in a small signal, boosts it up for logic purposes, and then you have loss. All that stuff I mentioned. You're going through the air, you're losing energy, you get scattered, you get absorbed. That's what that loss factor is. Here it's simple, we just call it L. In real life, loss factors are extremely complicated and can change minute to minute, temperature to temperature, rain or shine, night or day. We have advanced models for it though. So for our purposes, we'll leave it as L, but at the job, you're gonna have a very big computer that handles that for you. All right, so we've established the most important formula. All of this is just a derivation for this guy right down here, which is the power received. That's the most important thing out of this slide is just that last formula, the received power with the processing gain and loss. That is exactly what you're going to use to engineer around RCS. Because, as mentioned previously, RCS is right here, which means you're able to mess up the equation and you can solve for your RCS. In like a perfect world, in the real world, you don't have a chance in hell of getting RCS out of this equation, not a chance. If it was that easy, everyone would be great at stuff. Unfortunately, that's not the case. One of the reasons that things become a problem, and one of the amazing things that the human race has been able to accomplish, is make radars work at all. Because of this. Our world is full of noise. Not the acoustic kind, but the electrical signal kind. So this stuff is literally everywhere. It's omnipresent. You cannot get rid of it. Even if you got rid of every transmitter, every battery, every voltage that you could possibly imagine, it doesn't matter because temperature alone can induce random voltages inside of just materials. So you have no escape. So you have to deal with it. Because of that, we have waves. But the primary sources of noise that impact radar systems are clutter, which is just random stuff in the environment. A hill, a tree. Most advanced radar can even detect insects in the air, which is crazy, and they have to account for that. Then there's interference, unintentional and intentional. Someone else is on that frequency. Another radar's beam reflected and hits you. Even worse, someone's actively jamming you, which is a big consideration. And then there's the last one that I briefly mentioned, which is just standard Gaussian thermal noise. Heat results in random voltages in your circuits. It's really annoying to deal with, but it is a fact of life until you can get down to absolute zero, maybe you have a chance. Technically, the formula says if you get to absolute zero, you will no longer have thermal noise. You'll also have nothing, so that's good. And then interestingly enough, for most modern radars, the common limiting factor to detecting a target is thermal noise alone. All that other stuff, we can handle it easy. The thermal noise, we have no real solution. There's no filtering for it. If your target has a low enough RCS, you're hiding in what's called the noise floor, which is basically Anything that's weak enough to get down there just looks like noise. And there's a lot of technologies, including technologies from the lab that those two work at, actually no, you work at, that makes use of hiding inside of noise floors. But we'll keep moving. Now we get to take it into account, which is important. That thermal noise equation I mentioned is pretty simple. It's just the power of the thermal noise. Again, everything's in watts. That's Boltzmann's constant. Everyone may have heard of that before. This is just the temperature in Kelvin, nothing complicated. And B is the bandwidth. This is where you start taking into account the frequencies. Radars can operate at a wide band, but wide swath of frequencies. And most advanced radars can switch on a dime to different frequencies. And because of that, you have to take into account frequency, bandwidth, all the things you can do, and take into account that they can change it up any second. And we're going to get into why that's important in a bit. But bandwidth is super simple. My cursor was in the picture. That's not like an absolute value bar or something that I miss. It's just equal to the highest frequency minus the second frequency. It just gives you basically all the little frequency, sub-frequencies you can operate inside of. Nothing too crazy yet. Center frequency, it's nice to know, but it's not super useful. In this case, all it is just an average of your highest and lowest, just tells you the midpoint. Nothing crazy. System noise temperature. This is where you take your actual thermal noise and then the noise of your actual amplification system. This can be mitigated. The noise inside your circuits, you can provide filters and things like it, but it's still a thing that's important. So we wrap it all up into a system noise as opposed to just thermal noise. Then we get to our signal to noise ratio. This is the important thing. This is what determines that noise floor that I mentioned. Where if you're able to get your radar return, that power that we mentioned back here, if you can get this power low enough, you look like noise, and they can't do anything about it. And that's the objective. But their objective is to make this as small as possible, actually as large as possible, but their objective is to minimize the noise as much as they can. So the signal to noise ratio is the minimum power that you want to be able to receive, because power received is, as we just looked at, exactly what we're interested in, divided by the thermal noise power, again, in watts. So we already know this formula, we just looked at it. This introduces bandwidth, temperature in Kelvin, and the Boltzmann's constant. And then we can do a funny thing. Noise is actually what directly limits our range of the radar. And this is super important because the range of our radar is one of the single most important parameters that a radar has. I want to be able to see as far as humanly possible with as much precision as possible, but range is extremely important. We have radars that can see 20,000 kilometers into space, right? That is only possible if you have extremely good signal to noise ratios. If you don't got that, you have nothing. So all this is, though, is a rearrange of this whole formula, because this is your maximum range, the range of your target. That's all it is. So you just rearrange this whole equation. I mean, I could do it for you guys, but I think you probably get the point. I think this is still algebra at this stage. Shift it around, take your your root of 4, and now you have your max range. And then, whenever you're going to be talking signals and stuff like that, the most agreed upon unit is decibels. So in this case, we like to convert signal to noise ratio into decibels, and the way you do that is you take the SNR that you calculate and just run it through 10 log, and now you're in decibels. Standard 10 log scale. Alrighty. So here's where we're going to briefly talk about the information that we can get from that radar return. I hinted at this, but this is a more exhaustive list of the kind of information you can pull out of basically, and that's it, and then we get all this info out of it. So obviously, we get how far you are from me. We get how fast you're coming at me because of Doppler shift. We get the direction because of the phase shift and where my radar is. I have a GPS location where I know I am. Do a bunch of math to know where you are. Easy peasy. I now know where you're heading. Size of target, that's what RCS is about, radar cross-section. How big is this thing? But in this case, as we all know, or you're about to know, that can be deceptive. Shape of target, this is also really interesting. Because our radars aren't actually just a pulse, they're continuous, constantly sending pulse trains of information and storing and building up a model of what's coming, we can actually discern the shape. And intelligence agencies get us nice lists of these from our enemies, which we can then compare against and decide what the heck is this thing flying in my airspace, which is very helpful. And this one's actually really cool, moving parts. The way this works is that Doppler effect, as we said, can tell you how fast it's moving. But it can also tell you any other part moving relative to the vehicle itself will add additional Doppler shifts that you can use a funny thing called a Fourier transform to decompose out into signal components and analyze individually, which allows you to detect propellers, turbines, turrets, missiles, things like that. Which again helps you figure out what is my target. All right, radar time. We've set up all the information you need to know about how a radar works, signal to noise. Now we can start talking about radar cross sections. Here's the deal. Radar cross sections have only existed in science since about the 70s, have only been applied since about 75, and back then, it looked like a polygon. It was not very good. And they used a custom supercomputer that they built themselves. There is no human on the planet who is capable of actually hand calculating the RCS of a plane. It's too complicated. We use tools, just like anything else. MATLAB, these things. MATLAB actually has tools that can do this, funny enough. Not military grade stuff, but it's factored into electromagnetic suites, aircraft modeling suites, that kind of stuff. This is important to consideration. But today, we're going to go through a simple example that's also instructive to give you a pretty interesting property of radar cross-section that's good to know. And it's important to remember. So, we shall begin. What is the definition of radar cross-section? Pretty simple. The power reflected to the receiver, this per unit solid angle thing, ignore that for a second, I'll describe it momentarily, all over incident power density divided by 4 pi. So that incident power density thing, remember, we've got that Wi and that Ws, which then we decomposed into just power received, power transmitted kind of stuff. Basically, this per unit solid angle thing, what that means is there's FOVs and point of views. RCS, you cannot simply report, I give you a plane, you measure its RCS, you will not come back to me with a number, 1 meter. That's not how this works. RCS depends entirely on where you're viewing the plane from. If you view the radar as a laser, like we said earlier, to simplify it in your mind, and let's say the plane is perfectly reflective, depending on how I'm looking at the plane, it's going to reflect completely differently. If I hit the tip of the wing, the turbine, the tail, the fuselage, it's going to completely change its effect. So RCS is actually reported as a map per unit solid angle. So if you ever look up RCS and click images, you're going to see like a whole 3D graph of it and showing the power returns and spikes at each of these graphs, at each of these unit solid angles. So basically just think of it as whenever it's per unit solid angle, it's just which angle are you looking at it from relative to the vehicle. So hopefully that wasn't too confusing. And then this is commonly used in these two forms, most often this one, but this one has its value too. This is making use of electric fields. This is using those incident power densities we discussed earlier. And then of course it's the limit as the range reaches infinity of 4 pi range squared times this proportion. And of course the unit of RCS, just like anything else signals-wise, is often reported as decibels. In this case though, it's reported as decibels relative to the square meters because RCS, signature-wise, is actually just square meters. So in this case, we create this funny unit, dBSM, decibels per square meter. Again, what does that mean? Anytime you do decibels, it's just 10 log with the thing you want to turn it to decibel scale. So in this case, it's your RCS in square meters, shove it into 10 log, now you've got it in decibels, good job. If any of you have taken EE 308, that's a common quiz question. It's converting things to decibels. Yeah. All right, let's keep going. All right, characteristics of the radar cross-sections. It's comprised of a lot of stuff. It's very complicated, but there's 3 main things that we want to address. the frequency of the incident wave matters a lot. You're going to see that in a second with our example. The polarization also matters a lot. We will not be talking about that today because it's just too deep. And the target aspect, that's that unit solid angle thing. Where are you looking at it from? That's super important. We're not going to talk about that either because we're not just going to like pull up a model of a plane and just start hand counting based off of which angle we're looking at. But it's important to know, and this is how it's actually done. Real RCS, you will simulate first, but how it's actually done is they have massive anechoic chambers. They take a scale model, or sometimes the whole vehicle, depending on its size, hook it up to a big gimbal and orientate it in a bunch of ways, hit it with their own radar, measure it back. And that's how they gain that information. Now that information is highly classified. You're not going to get that stuff. But you can go on Google and like say, what's the RCS of the B2? And it will tell you like, it's a bumblebee, right? All right. These factors must be taken into consideration when designing both radars and the vehicles. Because our objective is our radars need to be able to see their stealth vehicles, but we don't want our stealth vehicles to be seen by their radars. It's an infinite cat and mouse game, so goes the defense industry. Right? All right, example time. We're going to set up a problem. So, if you're unfamiliar, this little thing is one of the accepted symbols for an antenna. Simple. We're going to call this a radar, whatever. This is the target antenna. And what I'm going to do is describe why we're using an antenna. Why aren't we using a square sheet, a plane, what's going on? So, the following example is going to illustrate some interesting properties of RCS, and it's actually going to illustrate an extremely important understanding as to why that frequency dependence comes into play all the time. So, I recommend following along and asking questions as I'm going. If there's anything you're confused about, feel free to ask questions. I'll do my best to answer. But we also have Q&A at the end if you would like to wait. So be it. All right. So, assume we have an antenna pointing directly, this is the antenna I'm mentioning in this case, pointing directly at the radar shown below. The gain and the effective area of this antenna is facing directly this way. So it's perfectly perpendicular, facing on. The laser of the radar is coming in, and my hand's the perfectly flat antenna looking at it. And the terminals of this antenna, because antennas have, not really a power and a ground because they're AC, but just two terminals of this antenna are shorted together. So all the collected power is re-radiated. That's a really complicated way of saying we've turned this into a radio mirror. Anything that hits it gets sent back. No attenuation. In real life, that's not how this works, but on paper, I can say whatever I want. So, set some rules. PT is power transmitted out. Same with that gain. Gain out, just a factor. Here's your range. The PC is the power collected, just what's going to be re-radiated out. Radar cross-section. The effective area of the antenna, that aperture area, square meters. Again, that multiplication factor, the gain, bounces it back out, which we receive as a power with an associated multiplication factor. Remember again, these are the same because it's the same antenna. This is a monostatic radar. All right, let's move on. So I keep that at the top for reference, but as we go, here's how we're going to start. So the radar receiver sees a return of that's the energy that it shot out and bounced back. We saw this formula already. This is all the way at the start. It's just the power returned after you pull out. In this case, though, we are going to leave out the loss and the, what was it? It was the loss and the, what did I forget? The processing gain. We're going to leave those out in this case. It's not helpful here. So we saw this already. Power transmitted, gain of that transmitter, that effective area over there of my target, effective aperture. This is just because this is an antenna. Normally that would just be the RCS. And then 4 pi range squared. Okay. Then we're back at me, the transmitter. Now it's a receiver. And we're looking at that scattered power density that our radar sees, that WR, receives power, which we're then going to convert into PR in a second. What's that? It's that PC value, so it's this whole guy right here, times that GA, which is him again. GA, PCGA goes this way. Again, divided by 4 pi r squared. So far, so good. It's still just that power and power density equation. Then, it yields the return power, which is what we're interested in, because that's where RCS starts coming in, of the power transmitted with the effective area squared of him, his area squared, times the transmission gain over there, times the received gain. So again, just like last time, those gains, because I sent it out and received it, same antenna, same gains. It's basically g squared, but we leave it just to illustrate that it's both. Then, we're going to do some comparison. We saw that original PR equation. That means these are the same. PR is equal to PR, same system. Which means we can do some math. So, for PR, we're trying to find a relationship between RCS and the effective area of my target. In this case, the effective aperture area. Same deal, if it was a square plate, it would be length times width. Then, we're going to observe this. We set the new formula we just derived, making use of our target, equal to the one we looked at previously. That involves RCS and wavelength. Set them equal to each other. PR is equal to PR. All right, now they're the same. Cancel out common units that you see on both sides. Divide them from one side, turn them to 1 on the other. What are we left with? Well, PT and PT cancel. GT, GR, 4 pi, 4 pi, all that stuff cancel, 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 except for one of them, because this is 4 pi squared, that's 4 pi cubed. R's cancel out. R to the fourth, gone. What are we left with? On this side, we're left with area squared. On the other side, we're left with radar cross-section times wavelength squared over 4 pi. Well, we want to know the RCS, not the area squared. We know that one already. Flip it around, and what do we have? Radar cross-section of this example is equal to 4 pi times the effective area squared over the wavelength. That's important. For a large efficient antenna, as mentioned, because AEA is that antenna area times the efficiency factor, let's assume that we're 100% efficient. It's just the area, right? Nothing crazy. If that were a circular dish, the area would be, what is it, pi r squared, right? So that's fine, which means we can say, of course, it was squared, factor this out, 4 pi times A over wavelength squared is equal to A. But what do we know? We know that the GR, the receiver gain, is equal, what do you know? 4 pi times area over wavelength squared, which means GR is this. Radar cross-section is equal to the gain of the surface gain, which is just this, 4 pi times the area related to the wavelength. These things don't change. 4 pi, constant. Area, hopefully, constant. And the wavelength, that can change. And it's in the denominator. So what does that mean? Radar cross-section is equal to this gain factor, which is dependent on frequency, and the fixed area of your target. For example, think back to that thing I mentioned earlier. 300 megahertz is equal, let's say 300 megahertz, same example, replace the antenna with an incident plate, 1 meter by 1 meter, 1 square meter plate. I shoot my 300 megahertz out. I didn't put it on here, but the math works out to say that 1 square meter, you would think that the RCS at its peak is 1 square meter. It is not. The RCS of 1 square meter plate at 300 megahertz is 12.5 meters squared, which means that a non-stealth coated surface, it could be a centimeter squared, can light up like a Christmas tree, depending on the frequency that they're using. Most K-band is 24 gigahertz. If you just plug, instead of 300 megahertz, 3 gigahertz into this equation, 1 square meter just turned into 1,250 square meters. That's like more, that's pushing the surface area of a Boeing 737. And that could come from 1 meter of untreated space. Now think about that, bring it down, be more realistic, say it's a couple millimeters, but say their radar is at 24 gigahertz. You still look huge. This is the problem that the Su-57 has run into. It actually has the radar cross-section of a Boeing 737. 5th generation fighter. All right, so that's an important thing. If anything that you take away from this, take away that higher frequencies can result in magnified RCSs. Simple relation, super important. That's the single most important thing to remember, because if you mess up doing your math, applying the coding, someone scratches it, you can have a huge problem when your plane gets shot down and you lose your pilot, which is not good. So, now we're going to get into the scattering mechanisms. We've seen that these equations have this concept of scattered power density. And as we remember, all the way back at the optics slide, there's this property called scattering. Reflection follows a very simple Snell's law kind of deal, or just law of reflection. It's just like a sinusoid relationship, or it's like a sine over sine angle thing. Transmission just gets sent on through. Absorption, you end here. But scattering, you went through and you get deflected at some angle, and that's dependent on the properties, the incident wave, all this kind of stuff. Scattering is what we're interested in, because that's the most common thing. If you take your radar and you shoot it up at a vehicle, most of that energy is just going to get deflected at the proper angle that it should and just end up on Earth somewhere else. Unless you have multi-static radar systems, you're not detecting that. We look for scattering. That's the most important thing, is scattering. Radar returns are predominantly scattering. All right, so there's mechanisms of scattering. To find the radar cross-section of a complex target, anything that's not a plate or a sphere, it's necessary to determine the total scattered electric field. Is anyone here familiar with finite element analysis? It's a tool and a concept used in mechanical design, thermodynamics, things like that, to model super complicated systems. How do I model a metal pipe that I'm holding fixed here and I'm bending it over here? How in a computer software is it going to know how that's going to behave? Well, we don't have infinite compute power. What we do is we break it up into tiny pieces and then plug it into a physics engine. That's what we're doing here. We break our vehicles, these super complicated vehicles, up into a bunch of tiny pieces, compute each one in a bite-sized manageable chunk, and then sum it all up. Per unit solid angle, of course. But simple-ish formula. E here is electric field strength. Is it volts per meter? Yeah, that's what I thought. Volts per meter. In this case, sigma, summation signal. N is just the amount of elements you're dealing with. And then you just do that absolute value of the electric field squared. And sum all of these. There could be hundreds of these, thousands. In most advanced computer simulations, there's millions, right? Thank God we don't have to do that ourselves. That's terrible. All right, but there are scatter sources. Reflections are going to yield your highest peaks. If you have a radar there and that reflection hits you, you just got a massive radar return, because that's going to lose the least amount of energy of the sheer reflection. So it's going to be really easy to see. So it's going to yield these highest peaks, but as we also said, what are the odds you got a radar there? So they're super rare. When you get them, they're great, but don't count on it. Diffractions are going to come from the edges of your wings, tips of your vertical stabilizers, that kind of stuff. They can be important, but they're easy to mitigate. So often you don't expect to get those either. Surface waves. These ones are a little hard to understand, but basically, planes have metal in them, and often their surfaces are made of metal. Aluminum, manganese, alloys, this kind of stuff, but it's still metal. Metal is a conductor. And because it's a conductor, if you hit it with an electromagnetic wave, it's going to excite electrons in there. What happens when you move electrons in metal? You make a current. What happens here is your plane basically becomes electric. You blasted it with radar. The radar energized electrons, created eddy currents, which are now flowing in random orientations around your vehicle, and they can go for loops and loops and loops until they stop. And the second they stop, they release a radio wave, which can be detected. These are super common, and they can be very large, and they're the most important one, second most important one to deal with. This one is the single most annoying. Ducting comes from jet inlets and similar structures, things that you cannot compromise on. Anything else, you can change its shape, add a coating. You don't get that freedom with an inlet. That inlet needs to be a certain diameter, a certain shape, to pull in a certain amount of air. And inside that inlet is the most bumpy, fast-moving structure you can imagine in the form of some type of turbofan or jet turbine. Ducting basically results where the radar is absorbed through the metal of the duct, or of the inlet. So we have a circle, comes in through the circle, goes through it via surface wave interactions, exits it, now it's inside an air gap functionally, hits this again, but now, because there's still a current flowing through here, because there's still radar coming through, it just starts bouncing around randomly inside here. And then it just sends out a bunch of radar returns coming out of your inlets. Anyone here familiar with what happens when you photograph a cat at night? Its eyes light up like a big fat LED. That is exactly how it looks when your inlets get hit with radar. It just shoots out in all directions, which is why it's super important to find ways around that. And one of the earliest ways that they did that is right here. It hampered performance. It was a trash vehicle, but this was covered in grates, which were coated in radar-absorbent material. And the grates were sized such that they would functionally act as a Faraday cage to the frequencies that they were worried about. But that's why this thing flew slow. The airflow it needed was not present. Go. Important to, oh, I went too far. All right. Yes, so that's important. Now, again, I mentioned that this is predominantly done by computer programs, which is why we're not going to do it. I'm not a computer. So we're going to just leave that be. This is important to note it. This is important to understand. So we've gone over a simple understanding of what RCS is, how to compute it for simple structures, its important relationship to frequency, and how, depending on the frequency, you might have a way bigger problem than you initially thought. You could have had a centimeter uncovered, now it's 10 meters. That's not good, right? So that's important. So the conclusion for this set of slides, or for this portion, is it's extremely complicated. There's a reason that this is one of the most classified things that you can actually get into in a professional context, because the amount of economic power that went into producing this type of technology, funding these researchers, giving the equipment necessary, anechoic chambers are extraordinarily expensive, is immense. And it's super easy to just steal inventions from other people, which is why classification exists in a lot of places. So I encourage any of you who took an interest in this particular portion to acquire this book. I promise I didn't write the book. I don't get kickbacks. But it's a really good text. I think I mentioned this later on, but I'll say it here early. As I mentioned, this type of stuff is classified at the high actual implementation level. Because of that, you've basically reached the point where if you Google this type of stuff, you will get almost no useful information. You'll get a couple YouTube videos, who read a Wikipedia page, and it's very useless. And there's not many college classes on this, because colleges have a lot of international students. ITAR exists. By law, we cannot export certain information. It doesn't matter if it's classified or not. If it's classified, not top secret, secret, unclassified, but if it is ITAR regulated, which if you go read the USML, US munitions list, everything's ITAR regulated apparently, you can get in big trouble. You guys may have remembered when you register for classes, there's a button you have to click that says, I promise I won't export my classes to countries on this list. You may not have gotten to read the list, but it's all of our enemies, military enemies. So, if you're interested, this is the right town to be in, but you have to bite the bullet and get texts like this, and then get a job in it if you really want to get, all in. Or do research. Those are your avenues. But those slides that I just went through covers barely 25 pages. This is a 400-page book. There is a lot to know. All right, chemistry time. Well, not really, because that's also classified. But we're going to move on to RAM, except I forgot that I put this one here. So we're going to talk about this one first. Target shaping. How many time? Yeah, we're good. All right. Target shaping. The first line of radar cross-section engineering is considered by many to be target shaping. What is target shaping? Well, it's exactly what it sounds like. You change the physical shape of the target. In this case, the target's actually your own thing. They just call it that. But you change the shape of your vehicle. You all saw the F-117. That thing looks like it was made in Roblox. It's terrible, right? Aerodynamic, not aerodynamic, unstable. They called it the hopeless diamond for a reason. And basically, this is super important. And it's one of the reasons why every single modern aircraft kind of has a look. Everything looks like an F-22. Everyone's stuff just looks like an F-22. Why is that? Because that thing is perfect. But even so, we're going to go real quick into, again, Snell's law. very simple. But important thing to note, shaping is a wideband solution. What does that mean? It is independent of frequency. We mentioned that there are things that are dependent on frequency. Shaping is not, because shaping is simply optics. This is when you can really roll back and rely on the simplification of just assuming it's like a light beam, because target shaping is directly using everyone's favorite physics 2 topic, Snell's law, which is basically the angular proportion of a reflection or refraction based on the refractive indexes of your material. That's a parameter that you get on a material basis. And then of course it's just sine and then your incident angle along with your exit angle, right? Common. And target shaping, while important, is not enough. Not even close. Here's some great examples. Every vehicle that the United States has that purports to have stealth capabilities is shaped oddly. That was the first one, and you can tell that thing was real wacky. This was the next one in the timeline. This is the famed B-2 Spirit. This is the stealth bomber, the world's only. And it's basically a flying Dorito. It's just a flat plane. And what's important to note is the flatter and smoother you can get, the better. Target shaping, if they could, every plane would be a flat disc. Not even a disc, really, but yeah, just be a flat disc and would just hover through the air. That's why UFOs exist now. But then the famed F-22, which is where everyone starts copying us. Because here's the thing, this thing was terrible, it was slow, it was good at its job, but it was slow, it could not defend itself, that kind of thing. This thing is great, but it is also slow, but they designed it very specifically, so its stealth is superb. You almost cannot see this guy on radar. This guy also is very stealthy, but it's a fighter. It has to have capabilities. It needs to be fast, agile, and it needs to be able to carry weapons. So Lockheed Martin came up with that design, and then everyone copied it forever. Basically every vehicle post the F-22, everyone was just like, that's the shit, and just went with that. This right here is a drone, actually, funny enough. And an important thing to note, radars are often on the ground. Remember that I mentioned that inlets are horrible? Radar cross-section? Notice where the inlets are on the stealth vehicles. They're above, on top of the vehicle. The inlets on the B-2, on top of the vehicle. The fighter couldn't do that one because it needs to be fast, so it sacrifices some stealth there. The drone, the inlet's up here. Why is that? Radars are on the ground. Radar's coming up at you. If your whole vehicle, stealth-coded, is blocking your inlet, you eliminate ducting as an issue. Is it ducting? Yes, you eliminate ducting as an issue, or at least heavily minimize it, which is super useful because it's horrible to mitigate otherwise. And you're gonna have to sacrifice a lot of performance, which is not something we like to do. All right, radar absorbent material time. Comes in several shapes and sizes kind of thing, but predominantly, the forms that you're looking at is a coating. In the case of the F-117A, it was literally paint, straight up. You painted it on. And then in the form of more modern aircraft, it's more of a jelly substance, a goo, still kind of painted on. Composites, nowadays we're starting to get into the advanced realm of where we can start replacing that pesky metal that reflects radar real good with composites that might be transmittable to it. It'll send it right through. Now, that's not actually as great as it sounds. There's a concept called radar penetrability, which is if your vehicle was this super lightweight carbon fiber composite, it still has metal engines, it still has metal circuits. You're gonna send that stuff, that radiation up through there, it's gonna go right through your composite, good job, it's invisible, and then hit your engine and reflect like, again, Christmas light. So they have their uses, but they have weaknesses. And artificial materials. Has anyone heard about any of the news articles last 10 years, where people start using like carbon nanotubes to like bend light and stuff? That's what that means. Light is electromagnetic radiation. Those carbon nanostructures and engineered nanostructures are fully capable of bending radio waves, which is the perfect solution. If I just coat my vehicle in that stuff, all the radio waves just bend around it. That's great. Except carbon nanotubes suck. They're terrible. You can't manufacture them. They're weak as hell. They're just shit. So unfortunately, we're not there yet. But if you want to make a lot of money, get on it. So The first mechanism behind radar absorbent material is absorption. Basically what that means is the energy came in and went nowhere. It got turned right into heat, which is good unless you start being too efficient, you make too much heat, and now I can see you with my infrared satellite, but that's a whole other problem. So the first mechanism is absorption, but they have three components of absorption. This is where the electrical engineering comes out. You have ohmic losses, which is exactly what it sounds like, ohms, resistors. Electrons get excited, move through the material, and lose their energy directly to heat. Perfect. And then there's dielectric loss and magnetic loss. These are a bit harder to explain, particularly if you don't have an electrical engineering background, because they're due to imaginary parts. In this case, whenever we're saying imaginary, we mean like complex. In electrical engineering, it's your J's, your square root of -1. In pure mathematics, it's your I's, right? And it's the imaginary parts of the complex relative permittivity and permeability. These are big words, they're not that scary though. The complex relative permittivity, which is in relation to electric fields, is this relative one, which again, relative is because you have material properties and then you have things like air, so you have to compute those. Minus J, your square root of -1, times again, ER. Right? And then complex relative permeability, is mu, which is, this is relation to magnetism. There's a slide that's about to explain a better understanding of these in a second. Again, minus J times it again. Complex plane stuff has its problems. It's a little difficult to understand sometimes. But in the case of things like this, there's a concept, everyone knows resistance, but resistance is actually just a part of something that is called impedance. And impedance is built out of resistance, and then it's built out of what's called reactance. So there's resistance and reactance. Reactance is like, think of it as the resistance of a capacitor or an inductor, which is basically the resistance of an electric field and a magnetic field. These things are real goofy, and there's a reason RF engineers make so much money, because it's horrible to deal with. But there's a pretty intuitive explanation for how this goes. All right, permittivity, permeability, big scary words, but what does it actually mean? People get scared when the Greek symbols come out. We all wish that numbers were the only thing in math, but they had to add the alphabet. It's whatever. So, electric permittivity, epsilon is the symbol, is a material parameter that lets you know how well a material polarizes in response to an applied magnetic field. Basically, all that means, if you just view a material, whatever it is, not everything behaves this way, but most things do, as a bunch of polar atoms, plus, minus, so it's all, think of it as bar magnets, but it's not magnetic, it's electric in this case. A bunch of polar electric charges. If you have a really good electric permittivity, the second an applied electric field comes in, all those random charges align perfectly with that applied field. Similarly, this is where people tend to understand better, is magnetic permeability, Greek symbol mu, is a material parameter that lets you know how well a material magnetizes in response to an applied magnetic field. This one's a lot easier. Everyone knows a material with high magnetic permeability. What is it? Huh? Iron. Yes, perfect. Iron has a magnetic, 99% ferrous iron has a magnetic permeability of 200,000. It's massive. So, all that means, same deal, think of it as a bunch of little bar magnets floating around in there, even though it's not, but it is. Good to think about. A bunch of these little guys, you apply a magnetic field, boom, they align up now. So if you're a ferrous magnet, or a ferrous material, when that applied magnetic field is removed, you actually stay magnetic for a certain amount of time. You can disrupt it by heating it up or dropping it, but generally if you don't add energy to the lattice, it will stay that way. If it's I'm gonna go real quick into a little tangent about all the different funny magnetic terms. If you're diamagnetic, that means your magnetic permeability is less than 1. 1's the standard, that's just air. And then when you go less than 1, and you can go real less than 1, like negative 200,000, if you get down to that, actually sorry, it doesn't go negative, it just goes down real low. But if you go backwards and go below 1, when you're a diamagnetic material, that's the definition of diamagnetic. when an applied magnetic field happens, you don't magnetize with the same way. You resist it. You produce a magnetic field that is the opposite. So it's almost as like you're shoving two, norths together. But the material itself without a field is not magnetic at all. And then the next thing is a good example of diamagnetic materials is just copper. Everyone's seen the example of drop magnet down copper pipe. Everyone's also probably seen the example of take big block of copper and like throw a magnet at it or something. It will generate, now to be fair, that's Lenz's law, but it still applies because copper does have a less than 1 magnetic permeability, hence it is a diamagnetic material. And then the last thing is a paramagnetic material. It's actually water is paramagnetic. That means it's close to 1, it could be above 1, but unlike ferrous, it does not stay magnetic when you remove the field. The second the field's gone, it's no longer magnetic. But funny enough, in a strong enough field, water is attracted to magnets. Interesting. That means you could lift a person, possibly. Has anyone ever seen the video of the frog floating in the 7 Tesla magnet in space? That's so funny. All right. RAM continued. All right, these are the losses that come from that magnetic and electric, magnetic permeability and electric permittivity. And basically all it is the ratio of those two for electric, same for magnetic. And then if you actually want to know the loss tangent, this is defined as the loss tangent, but if you ever needed to actually know the value itself, you would just do an inverse tan. And you'd get it. So, just like RCS, I sat down and we'll go through this real quick. The second mechanism behind RAM, that was all absorption. Wave comes in and turns to heat. All of that is absorption mechanics. Ohmic losses, magnetic losses, and dielectric losses. There's another mechanic just called destructive interference, resonance, that kind of stuff. This one is pretty cool. And it's really strong, except it has a weakness. Absorption is wide band. It's not that frequency dependent. It can be used across a wide spectrum of frequencies. This one, it can't. If you want to make use of destructive interference, which is a very efficient way to get rid of this type of stuff, to minimize and prevent the radar returns from occurring, you have to pick a frequency and stick with it. Because how it works, it's a little complicated, but basically radar and radio waves have a wavelength. What you do is you take a material and you make it, it's a special material, but the material itself isn't as important here, and then you make it the same thickness or some even ratio, as in wavelength over 2, wavelength over 4 kind of deal, and that's its length itself, like its depth of the material. And then when the wave comes in, it will then reflect off the back surface. That's why you got to pick the surface and the material a certain way to get that reflection. It will then come back, and it will come back perfectly 180 degrees at a phase. Which means that if you have two sinusoids, shift them 180 degrees and sum them together, they are now 0. Perfect destructive interference. That's how sound canceling works. Same principle. But it's narrow band. You have to pick a frequency because it's dependent on that width of material. So it has applications, and it is used, but you have to have a lot of faith in your intelligence about who you're up against and what their radar frequencies and capabilities are. This is also known as a resonant absorber. Fun vocab. So here's the deal. As we know previously, I actually counted 11 straight slides on just radar cross-section with all those formulas. And I think it was hopefully instructive, but in the case of this stuff, we're gonna have to stop here. One, because even this book, how good it is, does not help you too much with material selection, parameters like that, simply because, again, classified. But it does give you a lot of basis for how to compute these things, get your thicknesses, get your, calculate your ohmic losses, electric field strength, that kind of stuff. But here's the problem. Nobody's got time for this. No one has time for this. I have like 20 minutes left. That's not gonna happen, well, not really, but I do not have time for this. None of you have time for this. That is a terrible matrix. And that's, as he explained, the simplest version. That is the simplified example. That's terrible. That's horrible. If you take E308, you actually do this stuff though. As electrical engineer, that's what Dr. Port, great stuff. You guys may have trauma from those specifically. Now I should give you an even simpler example where a lot of that cancels to zero, but still. This is the exact quote from below this. To investigate the properties of lossless anisotropic dielectric, the Poynting theorem, blah, blah, blah. No one's got time for that, straight up. I wish we did, but the only way to really get into this would, one, have everyone already have taken EMAG so they can really understand it, and two, it would have to be its own entire presentation. So if you've taken EMAG and you want that, say it in the exit interview and I'll make one for you. All right, so shameless plug. Radar cross sections and stealth engineering actually has 4 pillars. There is target shaping, then there's radar absorbent material, but there's 2 more. And funny enough, in modern systems, radars are so good that target shaping has really lost its usefulness. We still do it, but it's not as great as it used to be. And our radar absorbent materials also do not cut it. Most radars can switch to multiple frequencies within milliseconds, even nanoseconds. Most systems start implementing things called chirps. Chirps are insane because it's a signal. If you've ever heard like a sound that goes woo, that's a chirp. Chirps is a signal, continuous signal with a massive amount of frequencies in it. So if I blast you with a chirp pulse, I hit all those frequencies at once, or at least very quickly after one another, which means all those narrowband solutions invalidated. They're not that useful anymore. If you just rely on target shaping and radar absorbent material, you will be shot down. They will detect you and you will lose. There's 2 more pillars: passive and active countermeasures. Nowadays, everything is actually this. So this is the next presentation, the next talk, which is basically a part 2 of this. It's 2 weeks from now, they're always 2 weeks apart. And it is Introduction to Electronic Warfare. They talk about that stuff in this book, but actually have an entire other book talking specifically about this stuff, which will basically be the basis of that presentation. Those 2 pillars I mentioned, those active and passive cancellation, a quick hint as to what that actually is you have insanely complicated and advanced arrays of sensors on board your vehicle. When a radar comes in and hits you, or really any detection, but really radar comes in and hits you, you sense it, you know its direction, you know its magnitude, you record the signal if they've got any sneaky stuff in there, and then what do? You have a computer right there that allows you to manipulate that signal and do with it as you see fit. Manipulate it, send it back, phase shift at 180 degrees, do that beautiful active cancel or that beautiful destructive interference we mentioned, and blast it right back at the radar and go completely invisible. That's really, really important, and that's the basis of most modern stealth systems. Straight, like that's the actual trick, except it gets even farther than that. We have systems called decoys. Everyone knows what a decoy is. Well, we want to trick someone, throw a noisemaker somewhere, they're going to go that way, not this way. Well, it's not as easy in the radar world, but we have done it. There is a very popular system called the ADB, or ADM 160 MALD missile. It is a decoy missile from the United States. It's a top secret kind of deal. It's on Wikipedia, so you just look it up. It is capable, it's a missile, it's a little cruise missile, it's got little wings, but it's small. It can be held by a plane and fired. It is capable of detecting radar from an enemy, manipulating that signal, and sending it back to them, and making the enemy think it is anything. It can manipulate those signals so precisely that it can give it back in RCS. This little missile can say, I'm an F-35, I'm an F-22, I'm a 737. It can just trick the radars. And it's actually super powerful, so powerful in fact, Ukraine's current offensive inside of Russia made use of 3 of them. We gave them some freebies. And that's what allowed them to get behind the lines, take out air defenses. We tricked all their air defenses to give them an opening. And that's kind of the basis of the usefulness of this type of technology. But in stealth, it is a must. Nowadays, everything's electronic warfare. In conclusion, we have discussed a brief history of stealth, detection methods, infrared, radar. Focus on radar is the most important one, but infrared, acoustic, sonar is its own thing. It's really only really important for submarines because we really actually use radar against boats too. We don't actually just sonar unless you're actually a submarine. Radar itself, radar returns, which is all that math. Radar cross-section, again, more math. Target shaping, briefly, the importance of it and how it works. Radar absorbing materials, and where to learn more, which is, the next slide. So you're hooked, where do you learn more? So if you are a UAH student and happen to have access to electrical engineering courses, these are the classes that will give you information and further understanding. And instead of a 1 hour and 20-minute lecture, you will have many 1 hour, 20-minute lectures over the course of a semester or two, which is way better to set you up with a career in this field as opposed to me. So, as mentioned several times, EE 308, this gives you the basics. This is electromagnetism, this is EMAG. There are physics courses at UAH that are equivalent to this, if you're physics. EE 421, antenna design and analysis. That is both for radars and for targets. You need to know that. Fundamentals of radar systems and radar systems. Again, we have whole classes, series of classes, dedicated strictly to radar systems. And that's because, again, this town is fundamentally built on top of radar systems. Again, call it out, very important. This text, Radar and Laser Cross-Section Engineering by David C. Jean, is excellent. It is from the AIAA Education Series. I recommend AIAA texts all the time. I have a collection of many of them. They're pricey. I don't recommend buying them willy-nilly. The full collection of like 300-something books is like $40,000 if you buy all of them. It's insane. But each one can be anywhere from $60 to $150, and they're very, very helpful. And if you have an interest in something, you can probably go search keywords on AIAA's website, and you will find texts about it. If you like missiles, they have entire series on advanced tactical missile design and guidance systems. They have multiple series. There's 7 volumes. I have several of them. They're very good. But there are various fields. I mentioned this, but we're going to go over it one more time. Various fields in science and engineering that are extremely important to modern defense. And many of these topics, advanced discrimination, which is, what am I seeing in this radar return? Stealth technology, guidance, navigation, and control, the books on the missile guidance, etc., are extraordinarily difficult to get into because they are very classified. They're the basis of modern defense. Everyone wants to have the best versions of this stuff. As of now, the United States does have the best versions of this stuff. So you're in the best place if you're interested. So, you basically, as Smith said, YouTube, Google, not very useful anymore. You have no choice. If you want to get into this stuff and start understanding what's going on, you got to buy books like this. They are all ITAR exportable and unclassified. So they're legal, they're fine. And again, the information is quality drops when it comes to topics like these. And if you want to really get into it, you're going to want to get internships and jobs in defense, which again, great town for it. So, I hope that was instructive. That's the sign out. Please fill out that form. Then we'll have the Q&A in a second. But anyone who arrived late, raise your hand. After that, I'll flip back up to the sign in, so you can sign in, just fill out that quick form. And once everyone's done with that, I'll switch to Q&A and I'll just stand around. If you got any questions or anything, feel free. Otherwise, thank you for your participation. Good stuff. You'll learn yourself a thing or two.
100%. As a computer scientist, a lot of that was, like 10, 11 years old since I've had like physics and stuff.
Like, you know,
yeah. So.
You're not crazy. Has everyone given it a good scan? All right. We'll roll it all the way back. I think it's like 41 slides. I gotta click it earlier. Woo, there it is. All right. Anyone who was not here at the beginning, quick sign in. Thank you very much for that. Alrighty. Oh, I did not mention it during the time because I forgot to put it on the slide. I was supposed to say it out loud, but then I forgot. We may have the best stealth at the moment, but we did not come up with it originally. The F-117, that funny polygon plane that everyone likes to make fun of, was designed by Lockheed Martin Skunk Works. They are pretty famous, but they did not come up with the physics and principles behind stealth. Who actually came up with it is one Peter Umfestev from Russia in 1962. He published a paper in Russia in 1962 titled Method of Edge Waves in the Physical Theory of Diffraction. He had nothing to do with defense. He was a pure physicist writing about wave theory. Just goes to show you, everything can be very useful in the right hands and the right money and budget poured behind it. The United States Air Force Intelligence Service found that paper, translated it, and made it available to Lockheed Martin for their bid. And it won them the bid. And now Lockheed Martin is the king of stealth, predominantly, except for the B-2, because we're better. Northrop Grumman. But...
Lies.
What do you mean lies? Get out of here, bro. Get out of here, bro. All right. But, everyone sign in, sign out. Good. No show. Thank you. Oh, click off.